So this is part two of reduced row echelon. So we're just going to continue. So let's move on to example 4. Okay. So example 4 says use RREF. Use RREF to solve this system. So what we have to do first is put it in. Let's convert this system of equation into an augmented matrix. So look at the columns and use the coefficients. So x1. So on the x1 columns, we have coefficients of 2 and 1. X2 columns, we have a coefficient of 1 and -1. X3 columns, we have a coefficient of 3 and 3. The equal sign can represent a straight vertical line. And then this is 0 and this is 0, right? So if we want to use RREF, we have to, our goal is to make this matrix looking like this. Right? We don't have to make everything, we don't have to make this number 0. We don't have to make this 0. We just have to make this, under this 1, we have to make this 0, and then above this 1, we have to make it 0. So what should I do first? So we have to start with this matrix, and I think I'm going to make this 1 into a 0. So how do I make that 1 into a 0? By using row of operation. And I'm more specifically, I'm going to do row 1 minus 2 times row 2. Okay, so I kind of looked at the number 2 and 1. I looked at the denominator. The LCD is 2. You just have to make one positive and one negative. So the only way to do that is multiply the entire row by the scalar -2 and add row 1. Okay, so let's see. What's the first number in row 1? 2 minus 2 times row 2. What's the first number in row 2? 1. So what's 2 minus 2? 0. So this is 0. Continue the process. Second number in row 1 is 1 minus 2. Second number in row 2 is -1. 1 minus 2 times -1 is positive. -2 times -1 is positive 2 plus 1, that's 3. And then continue. Third number in row 1 is 3 minus 2 times 3. That's 3 minus 6. 3 minus 6 is -3. Okay, straight line. And then last number. Last number in row 1 is 0 minus 2 times 0 is 0. Okay. Okay, and then what we're going to do is we didn't mess with row 1, so I'll rewrite row 1. Okay, now what we'll do is, what should I do is, don't worry about this. Do not make this 2 into 1. We could do that at the very end. What I would do is, and don't worry about this making it into 1. What I'll do is we'll do the hard part. We'll make this 1 into a 0. So to make that 1 to a 0, you're going to do row operation. So to do so, you would have to multiply -3 times row 1 plus row 2, right? Because you kind of see the LCD between 1 and 3. The LCD is 3. You just have to make one positive 3 and -3. Okay, so -3, first number in row 1. So you start with the previous matrix. So now you start with this one, not this one, right? So first number in row 1 is 2, plus first number in row 2 is 0. So that would be -6, right? And then second number in row 1 is 1, plus second number in row 2 is 3. Negative 3 plus 3 is 0. And then negative 3. And then third number in row 1 is 3. Plus third number in row 2 is negative 3. So that's negative 3 times positive 3 is negative 9 to negative 12. Okay, continue. Last number in row 1 is 0. Plus last number in row 2 is 0. So that's 0. Okay, we didn't mess with row 2, so just rewrite it. 0, 3, negative 3, 0. Okay, now what I would do next is, so I think we're good. These numbers are fine as negative 12 and negative 3. So now I just have to make this number into a 1 and make this 3 into a 1. So we can multiply scalar, and with scalars, you can do it more at one at a time, right? Yeah, so to make this negative 7, 6, to make this negative 6 into a positive 1, you're going to multiply by the scalar negative 1, 6, and you're going to multiply that by the entire row 1. The same thing with negative 3. Get rid of that make this 3 right here, not that negative 3, into a positive 1, you multiply by the scalar 1/3 and multiply by the entire row 2. Okay, so just FOIL out this negative 6. So negative 1, 6 times 6 is positive 1, 0. And then negative 12 times negative 1, 6 is 2, 0, right? And then FOIL out this 1/3. 0 times 1/3 is 0. 3 times 1/3 is 1. Negative 3 times 1/3 is negative 1. And then 0. Okay, now we have it in the goal form, right? We have these ones are diagonals, are pivots. We have these 0, and then we have these numbers. So now we can find out our solution. So we have to do some back substitution. So remember, this column is x1, and then this column is x2, and then this column here is x3, right? So if you look at this second last row, it would be 1 x2 minus x3 equals 0, comma, and then this would be 1 x1, and there's no x2 because it's 0, and then plus 2 x3 equals 0. So yeah, you're gonna have to do some. So over here, if you kind of move, if we solve for x2, you would have to add x3. So this would be x2 equals to x3. And then I guess you can replace, and over here, if you solve for x1, you would subtract 2x3. Okay, so so since x2 equals x3, that is a free variable. You could say that x3 is a free variable. And this just proves that the solution is infinitely many. So the answer for this one is this, you have more than one solution or is infinitely many. Yep, the solution is infinitely many. Example. So example 5, use the row reduction RREF algorithm to solve the system. And why did I not write the problem? Okay, so let me write the problem. So we have x1 here. Okay, so here's our system equation. First step is write it as an augmented matrix. So it's going to be 1. So look at the column x1 and use the coefficient. So it would be going down vertically, it would be 1, -1, 2, and 3, right? And if you look at the column x2, we have -1. Over here, we have a blank space, so that's going to be 0. And then you have -3 and 2. And then if you look at the column x3, our coefficients are 2, 1, 5, and -1. And then straight line means vertical line. And then ours are 4, 6, 4, 6, 4, 1. Okay, so if we're going to do RREF, that means we have to make our pivots all ones and everything below ones. Everything below ones and above ones should all be 0. So our goal is going to be, we're going to somehow convert this matrix as this. Uh, okay, so we actually want this to be 0. because yeah. So what? Yeah, we want this last number to be 0, not a number, and we want this entire. So basically, we want this whole row on the bottom to be zeros if we're going to do RREF. So what would I do first? Let's start with here. Do you see this -1? I I really just want to get that 0. So all you got to do to make this -1 to a 0, you add row 1 and row 1 and row 2. So it's going to be row 2, and you add row 1 plus row 2. I'm not going to show the work because there is a lot of steps, but you could do the steps one by one, but I'm just going to put the answer. So when you add row 1 and row 2, you're going to get a new row 2, and that new row is going to be 0, -1, 3, and 10. But by yourself, you do have to do the work, and you have to be careful not to make a mistake. And then we didn't mess anything with row 1, so rewrite row 1. And then this is 2, -3, 4. We have 3, 2, -1. Okay, then what I want to do is see this 2, I want to make it into a 0. So what to do is you can add row 3 minus 2 times row 1, and that'll give us your new row 3. So you start with this previous matrix. It's going to be row 3 minus 2 times row 1, right? And when you do that, your new row 3 is going to be 0, -1, +1, straight line, -4. Okay, and then we didn't mess with row 2. We didn't mess with row 1, so it's going to be 0, -1, 3, 10, 1, -1, 2, 4. And then this number, we didn't mess with this row, so it's 3, 2, -1, +1. Okay. Then the next step I would do is see this 3 here, I'm going to make that into a 0. So to do that, you're going to multiply 3 times row 1 minus row 4. So it's going to be 3 times row 1 minus row 4. And that gives you your new row 4. So when you do all the work, you should get 0, -5, 7, straight line, and then 11, right? And then we didn't mess with any other rows, so rewrite it. So this would be 0, -1, +1, -4, 0, -1, 3, 10, 1, -1, 2, 4. Okay, then what you would do next is mess. Okay, now I got all these zeros. Now I'm going to leave this -1 alone because I can multiply it by -1 at the very end. So what I would do next is I think I'll make this -1 to a 0. So how would I make this -1 into a 0? I guess you can multiply -5 by row 3 plus row 4. So this -1 is technically in row 3. Okay, and -1 in row 3, so it's going to be -5 row 3 plus row 4 gives you your new row 3. So that's going to be 0, 0, 2. This is going to be 31. And this is going to be 0. Next is make this -5 to 0. So how would I do that? I would multiply -5 by -5 row 2 plus row 4, and that'll give us, that will eventually make this -5 to 0. So -5 is technically in row 4. So it's going to be -5 row 2 plus row 4. And that'll give us your new row 4. So when you do all the work, you're going to get 0, 0, -8, straight line, -39. And then we didn't mess with row 4, row 3, or we didn't mess with the previous row, so just write it down. 0, 0, 2, 31. Perfect. Okay. Now what I do next is I want that, remember we want this whole row to be 0, so maybe I would try to make this -8 into a 0. So is that, can I do that? Yes, I can. I could do 4 times row 3 plus row 4, and that'll give us your new row 4. And you'll see why I did this first. So when you do all the work, you get 0, 0, 0, straight line, and then this would be 85. And then this is going to be 0, 0, 2, 31, 0, 8, 1, 3, and so real why I did this is we want, this would be false. Remember this is x1, This column's x1, this is x2, this is x3. You can't say 0x3 equals to 85, right? That would be false. You want this whole entire row to be 0. There's no way I can make this 85 0 by using another row of operation. So what that means is it's no solution and inconsistent. Okay. So now you have okay, so now you have a good idea how row of operation works. So now let's talk about existence and uniqueness theorem. So existence and uniqueness theorem, a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot point column. Um, if a linear system is consistent, then the solution contains either. So one, a unique solution, no free variables, and two, infinitely many solutions, at least one free variable. So let's look at example 6. We have this matrix, and it looks like it's a 3 by 1, 2, 3, 3 by 4. Right, so this matrix is 3 by 4, and we want to know if if it's consistent or inconsistent. Um, so what is inconsistent? Inconsistent is no solution, right? I think this would have a solution and it would be consistent because you could call this column x1 or xyz or x, or call those column x2, x3, etc. So this would be x3 equals to 2. This would be x2 equals -3. And then this would be x1 equals to 5. So yeah, this would be consistent and unique. Okay, let's look at matrix B. So this is what is this matrix? This is 3 by 1, 2, 3, 4, 5, 3 by 5, right? And we'll call this column x1, x2, x3, x4, right? So let's see here. This one is 1x4, so it would be x4 equals 7. This one would be x3 equals 5. And then this would be x1 plus 6, x2 equals to -1. So is this going to be consistent? Will this be consistent or inconsistent? What is x2 going to be? Um, we know that this is x4, 7, x3 is 5, and then this is x1 plus 6, x2. Mm, I think x2 is going to equal to x2. That makes it a free variable. Yeah, I think if you solve for it, here's you have x1 plus 6x2 equals to -1, and then you solve for x2. Um, I'm gonna, yeah, I think x2 is um, a free variable, so that's like infinitely many. So I do think this matrix does have a solution. It's consistent, and it would also be infinite. Yeah, so consistent and infinite. Okay, so this does have a solution, and it's just many. It's a solution, and there's just more than one solution because of this free variable. Okay, let's look at C. We have x1. Oh, what kind of matrix is this? This is a 3 by 3. It's a 3 by 3 matrix. This is x1. This is x2. So if you look at this x2 or 0x2 equals to 1, that's completely false, right? 0 does not equal to 1. That's a false statement. So yeah, it's going to be inconsistent. You can stop there and just say it's inconsistent. Okay, let's look at D. This is a 1, 2, 3, a 3 by 3. And yeah, look at this last row. So this is column x1, this is column x2. So this is like saying 0x2 equals to 0. It's a true statement. 0 does equal to 0. So, and then if you look at this, this would be x2 equals to -2, and then x1 equals to 4. So because of this 0 equals 0, it's going to be consistent. So it does have a solution, and it's going to be unique. Okay, example 7 says, what is the largest possible number of pivots? So pivots are those diagonal ones of a 4 by 6 matrix you have, and why. So if you want, you can kind of draw this matrix 4 by 6. So 4 is the row, and 6 is the columns. If you kind of like drew it, it would look like this. Here's row 1, row 2, row 3, and row 4, right? And then this column is x1, x2, x3, x4, x5, and then the vertical line would be your x6 column, right? Or your B, yeah. So if you kind of, so this one would have a 1, right? This is your pivot. And then x2, row 2 would be 1. And then x3, r3 would be 1. And then x4, r4 would be 1. So this would be your diagonals or your pivots. So that means you have 1, 2, 3. We have 4 pivots. 4 rows, and one free variable. Okay, so let's look at B. What is the smallest number of pivots of a 4 by 6 matrix can have? Um, so 4 by 6. What is the smallest number? So if you want, I'm going to just draw it again. So the one. This is the smallest number of pivots. So let's say this, I think it would just be one because and what is, so they're asking what is the smallest number of pivots matrix can have. So you would have one pivot, right? I think, yeah, because this would pivot is like the one. So this could be in row two, this could all be zeros. This entire row two could be all zeros. And then this entire row three could be all zeros. And this entire row four could be all zeros. So you have one pivot and four free variables because you can have 4 rows. You can have 4 rows that's all zeros, right? So row two, row three, row four could be all zeros, and then you have to have um, a one right here. So that would be the largest. I mean, what is the smallest? Yes, one. What is the smallest number of pivots? It would be one. Next, as example A said, example 8 says, what is the largest possible number of pivots of a 6 by 4 augmented? So augmented uh, matrix in half. So how would we draw this? Right, 6 rows. So that would be one, row two, three, row four, right, and row six. And call this, oops, this one, x1, x2, x3, 3. So if this is an augmented, the last column would be your B. So it says, what is the largest possible number of pivots of a 6 by 4 matrix? So it's your one. So this could be a pivot. X2 row two could be a pivot. X3 row three could be a pivot. And I think that's it. You can't go any larger. So they're asking what is the largest? So you would have at most three pivots and 3 variable columns. So we didn't have 4 columns can't have a pivot at the wrong spot. Okay, so yeah, we'll have three pivots and three variable columns. Okay, D says, what is the largest possible number of pivots of a 6 by 4 coefficient? So coefficient matrix can have. So what is the difference between a coefficient and a augmented? It means the difference is it's kind of now it has like it's really 5 columns. So if you do so this would be 6 rows. 1, 2, 3, 6. Right? We have 6 columns. And because it's a coefficient matrix, not an augmented, the last column would be numbers. So it's actually 5 columns. That makes sense. So this would be column 1, column 2, column 3, column 4, and then vertical straight line. And then this would be numbers, right? So this time, um, pivot. So x row 1 x1 would be a pivot. X2 row 2 x2 would be a pivot. Row 3 x3 would be a pivot. Row 4 x4 would be a pivot. So this time you'll have 4 pivots. 4 columns slash variables. So yeah, in the coefficient matrix, um, you have an extra column, 2, 3, 4. So it's really 5 columns. Okay. Yep. Yes. So that wraps it up for this last example. And the next one would be vector equations or matrix algebra. I'm going to stop here.